this is basically a process of inelastic scattering. And what happens here? Basically, this is a process of inelastic scattering in which a charged particle transmits energy to the nucleus through electromagnetic interaction. And you see, this process can happen at a much lower energy than necessary. So basically, let me add, this process can happen at a much lower energy than necessary for the particle to overcome Coulomb barrier. So this means that in this entire process of Coulomb excitation, there is no role of nuclear force. Understand what is happening? Basically, what I am trying to say is that suppose a projectile comes and interacts with a target. Now, if this is the, say, nuclear field near the target, very close to the nuclear, this you can see is, say, of the order of Fermi-meter range. So this is the range of nuclear force near the target. Now, if the energy of this projectile is not very high, if this is not very high, then what will happen? Then the projectile will never come close to the target itself. The same projectile, it can never come close to the target, and this means that the projectile never reaches the range of the nuclear force. However, this entire region, the projectile will feel the Coulomb force, the electromagnetic force of the target. This black lines is the Coulomb force of the target. So this means that even in this scenario, when the projectile comes quite close to the target but still far from the range of the nuclear force, then there is basically interaction via your Coulomb interaction between the projectile and the target. And during this electromagnetic interaction between this target and the projectile and the target both can get excited. This is basically inelastic excitation, and this is happening through electromagnetic interaction. Okay, so basically what we are talking about here is inelastic scattering. Normally I have been talking about inelastic scattering as a result of nuclear force, but this is the inelastic scattering as a result of Coulomb force, no nuclear force. Okay, and this inelastic scattering, which happens as a result of Coulomb force, no nuclear force, is known as Coulomb excitation. Okay, so this is the basic idea. Now you must be wondering, sir, what is the importance of this Coulomb excitation? Because now we are taking a detour. We have been talking about various types of nuclear reactions, but now all of a sudden I am talking about the importance of, say, electromagnetic interaction in exciting both the target and the nucleus? Well, the reasons to study is quite important as well. So what happens is that, you see, the reaction mechanism is pretty well known, right? Electromagnetic interaction, no nuclear force. And this is basically, you can call it as an inverse of electromagnetic decay. So this is basically an inverse of electromagnetic decay, this Coulomb excitation process. Now, it is experimentally observed that very strong Coulomb fields can be created. Experimentally, very strong Coulomb fields can be created by bombarding nuclei with a beam of heavy ions. This is important. This is the zone of heavy ion physics. So, with this advantage, coupled with the precision that can be achieved in charged particle experiments, we have basically a very important tool to investigate the detailed features of the nuclei without going into the hassles of the nuclear interaction. Okay. Now, let me tell you in a semi-classical way again the basic idea about when you will consider a Coulomb excitation to take place. When will you consider? So, suppose a projectile, we have a projectile having charge small z. Okay. Now this approaches a target which consists of capital Z protons. So small z and capital Z protons in the target. Now you see the strength of the Coulomb field between these two particles may be characterized. So in this case, the strength of Coulomb field may be characterized by the Sommerfeld number. What is this number? The number is defined as eta equal to 1 by 4 pi epsilon 0 into this small z into capital Z E square, that is the product of both the charges, into H cross into V, or this is basically your alpha small z capital Z C by V, where this V is the velocity with which one particle approaches the other when they are separated by very large distance, and alpha is the fine structure constant. Now you see, classically the distance of closest approach
alpha की
fine structure constant. So let me again write it down. Alpha is basically fine structure constant, okay, and V is basically the velocity with which one particle approaches the other when they are separated by very large distance. Keep this in mind. Okay, now classically let us talk about the distance of closest approach. Let us call this Rs. So we will get this value of Rs from this condition, 1 by 4 pi epsilon 0 into small z capital Z E square by Rs, when this is equal to half mu V square, right? This we know. Potential equal to kinetic. Okay, this is the energy at the distance of closest approach, hardly any kinetic energy, and this is the kinetic energy at very large distances. And mu is of course the reduced mass of the projectile in the center of mass. Now, in terms of the Sommerfeld number, we have basically half of Rs is equal to alpha h cross c small z capital Z divided by mu V square. This is equal to eta h cross by mu into V. So, if this is the expression, so you see that the Sommerfeld number may be viewed as the ratio of half Rs and the reduced de Broglie wavelength. What is that? The reduced de Broglie wavelength, which is basically lambda by twice pi, which is 1 by 2 pi h by p, which is basically h cross by mu into V. So see, this eta is basically half Rs by de Broglie wavelength reduced. Now, what does the value of this eta mean? So basically, a small eta means that Coulomb field is weak compared with the available kinetic energy in the scattering. Fine. Now, under such conditions, the wave function of the incident particle, so if this is the such, so under such conditions, the wave function of incident particle is not greatly modified by Coulomb field, and so the Born approximation can be applied. On the other hand, if the Coulomb excitations we are primarily interested is on the opposite limit, that is eta is much greater than 1, then what happens? Then in this case, two particles, just a second, okay, yes, so I was saying is that if eta is much greater than 1, then what? So in this case, two particles are never close enough to each other for the nuclear force to play a role. And then in this case, the excitation of target or projectile is accompanied entirely through the Coulomb force. Okay? And such a process is called Coulomb excitation. So this is the case, that is when the Sommerfeld number eta is much greater than 1. See for yourself, eta is basically half Rs by lambda cross B. see, eta is much greater than 1. This means that this half of the distance of the closest approach, rs, that is rs is much greater than the reduced de Broglie wavelength. And this is our region of Coulomb excitation. This is what we will be talking about, Coulomb excitation. So this is the condition that corresponds to Coulomb excitation.